let's learn about the quotient rule. The quotient rule helps us find the derivative of, strangely enough, quotients. In other words, when we have fractions, functions that are fractions. So, for example, if I have f of x defined as some function divided by some other function, then the derivative of f is going to be a prime b minus ab prime over b squared. In other words, the derivative of the function on the top times the bottom function as it is minus the top function as it is times the derivative of the bottom function all over the bottom function squared. We're not going to derive this today, but there's a kind of a cool way that you can use the product rule to prove that this is true. Okay? That might be a fun challenge for you to try to come up with the quotient rule using the product rule. Here's our first example. So the top function, which I'll call a, is 5x plus 1. The bottom function, which I'll call b. So let's just do our product rule. It's the derivative of the top times the bottom as it is minus the top as it is times the derivative of the bottom all over the bottom squared. I hope you've noticed that the product rule looks very similar to the top of the quotient rule, except for the minus, right? So the quotient rule is like the product rule, except there's a minus there, and then you're dividing by the denominator squared. Here we go. So I'm in a Leibniz kind of mood. So the derivative of y is dy dx. Big fraction line. So the derivative of the top is 5 times the bottom as it is, x squared minus 3, minus the top as it is, parentheses are necessary here, times the derivative of the bottom. The derivative of the bottom here is just 2x, divided by the bottom squared. Da 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 da! That's my derivative. Now, we often will simplify or clean up the derivative, and this part tends to be the most confusing part. If I just have polynomials or power functions, usually simplifying means just distribute and combine like terms. So let's do that here. I'm just going to distribute that 5x squared minus 15. The tricky thing here is I'm distributing not just the 2x, but also the minus. So that's something we have to be very mindful of. So this is going to give me a minus 10x squared and a minus 2x. Right? I distributed the negative to both of those and the 2x to both of those. And usually, if that's a binomial that's squared, we do not expand the binomial out. We leave that as just a binomial squared. Now I think you can see we can just combine like terms. Negative 5x squared. I'll write this in standard form. And this would be my derivative in simplified form right here. Okay? So I took the derivative using the quotient rule, and then this is the derivative right here, but then I just combined, I distributed, I combined like terms. Let's find the derivative. This is a quotient, it's a function divided by a function, so the quotient rule is going to be our tool. Here we go. Pretty straightforward. The quotient rule is pretty straightforward once you get used to it. The derivative of the top, the derivative of e to the x is just e to the x. Don't you love that? Times the bottom as it is, minus the top as it is, e to the x, times the derivative of the bottom, all over the bottom, squared. All right. Now in this instance, when I am simplifying x squared squared, I am going to simplify that. I'm just going to call that x to the fourth. When you raise a term with an exponent to an exponent, remember you multiply those exponents. And this is an interesting thing now. So I'm now out of the realm of polynomial power type functions. So how am I going to simplify this? Again, simplifying in calculus is a little unclear, but what we often do in this situation is to factor out a common factor. Both of these two terms have an e to the x. Both of these terms have an x. So often the standard protocol is to factor out a common factor and leave your answer thus. But this is certainly the derivative, and this you could leave your answer like this if you wanted to, although normally we would put the 2 in front since it's kind of a coefficient. But often you will see things factored in this way. Let's try another example. Again, we have a quotient, a fraction. So I'm going to use the quotient rule. Here we go. The derivative of k. Ah, interesting. The derivative of 2. Well, that's just a constant. The derivative of 2 is 0 times the bottom as it is. Minus the top as it is, times the derivative of the bottom. The derivative of sine is cosine, all over the bottom squared. Okay, so let's just simplify this a little bit. 0 times anything is 0, so this is just going to give me negative 2 times the cosine of x. And if you recall with trig, we usually put the little exponent right there. Nice! Let's look at one more example. Now, the one danger of the quotient rule is that people launch in and use it whenever they see a fraction line. Could I use the quotient rule to take this derivative? Yes, I could. Do I need to? No, I don't. Why not? Stop the video and see why you don't need to use the quotient rule here. Yes, you're right. Instead of using the quotient rule, I could first just rewrite this. Remember, this means x cubed divided by x, which is x squared, minus 6x squared divided by x, which is just minus 6x, plus 7x divided by x, which is just plus 7. Wouldn't it be a whole heck of a lot easier to first rewrite or simplify this function and then just use the power rule? Yeah. Now, if you had gone through and used the quotient rule, you would have gotten the same answer, but it would have taken a lot more time. Baby.